For today, we at least are interested in the comparing or establishing equivalence of some invariant metrics in the regional classes of the bounded domain. So today I just want to share some of the references with the calculation recipe that Alan's are and I am very familiar with to proceed the calculation to get something done. The primary reference today I want to basically share is this paper, one of my paper of mine. The goal of this the paper is to proceed the calculation with the explicit form of the Bergman corner, which I just use the norm form to say something regarding the invariant metric. So let me just first give you the consequence. What one can tell here is that in this the paper, this paper concerns so-called the symmetry by this. So let me first give you the form of the definition. So the symmetry by this, so usually written in G sub 2 in the the literatures of the several complex variables, is a set consists of the first component written by Z1 plus Z2, and the second component written by the product indeed is come from the symmetry the polynomial in the just a two the components case. So and Z1 and Z2 are from the unit disk in C1. So then there's a very the important the remark on this the set. This is never biholomorphic to any convex domains in the C2. And also it is never exhausted by the convex subdomains. That's not possible. However, Kobayashi and Carathéodory are the same, exactly matched. So this is one important the example that provides the the counterpart of the Lampert theorem. If the convex domain is given, then the two invariant metrics are the same. What if the two invariant metrics are the same? Does not imply it should be biholomorphic to convex domain because of this counter example first. And also for not just the symmetry by this, for in general symmetry polydisk, the Bergman corner, I mean the explicit form are already known. So what I do in this paper is to proceed the calculation of the holomorphic sectional curvature with respect to the Bergman metric. And then I just conclude from the calculation. So this represent the holomorphic section of the Bergman metric with respect to the one arbitrary unit vector, and holomorphic sectional curvature sit inside of the negative range. And once one confirm this, then by using the theorem of Wu and Yao, one can conclude that Bergman, Kähler-Einstein metric, and other two invariant metrics are all equivalent by the constant depending on the dimension and the curvature range. So this is one the important one the implication. Of course, there's also another proof in the case of C linear convex domain that so it satisfies the uniform skew property. So it also works for the symmetry by disk. So that this conclusion also follows from the work of the uniform skew property as well. But my the intention, actually I didn't knew that result when I work on this, but my intention is to establish one concrete way of the calculating something concretely to say something interesting. That's the what I wanted to do. And before talking about the recipe, I want to just point out just a few things. It might be already known, but probably not for certain cases. So for example, so this is the one paper that was the about the important the implication about the horizontal sectional curvature of the Bergman corner. So in the case of the annulus in C1, also the Bergman corner form is explicitly known, at least in terms of the power series, so that what this paper did is also proceed a concrete calculation. Let me try to see this. Sorry, I need to look at this paper. Just yeah, this one. Just, let's look at this. So about this paper, look at this one. So this should be the form. I think so. Let's see. Yeah, this is the form of the holomorphic sectional curvature with respect to the Bergman metric, and this is just nothing but a Gaussian curvature because it's just a real surface. And the form of the Bergman corner is explicitly known, so that by using this form, then one can calculate the polar sectional curvature. So this is an important like the part of the example in a sense that from the general theory of the Kobayashi, it's known that the Holorn sectional curvature of the Bergman metric, so the range of the Holorn sectional curvature value is from negative infinity to positive 2 from the general theory. And this is the first example as far as I know. And I don't actually know any of the other example that exactly match with the full range of the Holorn sectional curvature. So two things. Holorn sectional curvature of Bergman metric, in general, has a range from negative infinity to positive 2. And this annulus indeed match that full range. And this is the only example I have that satisfies this full range. And it once it hits the inner like the circle, it goes to negative infinity. It goes to the outer circle. It seems it also hits the positive upper bound, positive 2. So yeah, so this is the important like the implication implication here. And this is just coming from the just really calculation from the explicit form of the Bergman corner. Even though this is, in my perspective, a little bit surprising in a sense that this form is not really explicit in some sense because it wanted to still deal with the power series in this expression of the Bergman corner. And if one also know the Szego corner, for example, from this paper, for example, Szego corner, then you can see that also the similar form of the Sigo corner is also known. So that one can expect that one can also proceed the similar calculations to see what would be the similar like the consequences as we saw last like the week. So one of the important question is that what's the geometric fundamental difference compared to the Sego geometry and the Bergman geometry? I believe it should be similar, but so because of the less importance than the Bergman corner, probably seems people might not calculate this yet. I don't know. So now you see my at least intention that by using this form, still one can proceed a similar calculation as this like the paper. So that the recipe from now on shares so might bring something new. So now let me just go back to my paper if you do not have any other like these suggestions. So the way of the calculating the curvature is a little bit subtle, a little bit subtle. So if you think about this like the domain, this domain is complex dimension 2. So in order to calculate the curvature everywhere on the point, one need to introduce the four real parameters. But this is really in handy. So one can use indeed the property of the invariant matrix. What's the invariant matrix? So any automorphism should be the isometric. So that also works for the Bergman metric as well. And now we have an explicit description of this domain. So what one can just check is the automorphism group of the G2 is already known. So I just cite this known result. So the any automorphism of the symmetry by disk is written by the first this map. Let me call it by the psi. So psi is just nothing but the map from D cross D to G2, just a map in the natural way. For each Z1 and Z2, it maps to Z1 plus Z2 with just a product. So this is just a natural map and composed with just a Möbius transform in the unit disk, but make sure that this H should be the same for each component. So any automorphism should have this form. So this is one like the handy like the expression that one can use. So by using this guy, then we can indeed naively think about this way. So that because this map is clearly surjective, so in order to investigate the point on G2, one can just investigate arbitrary point on D cross D. As long as we have this map explicit, then we know the automorphism group of this D as a just Möbius transform. Then what can we use? We can use it, but just nothing but the rotation. So the two techniques can be used. So we know by using the Möbius transform, we can map any point of the D to at the origin. We can map any point to the origin first. And for other like the points, we can just use the rotation to sit that inside of the real line, so that one can always like make the point that each point can be just sit on the just zero, so zero with some real value and map it so that this is always guaranteed. So for arbitrary points, of the G2, then by using the two properties of Möbius transform, one can map arbitrary point to the origin. And for the rest of the point, we can still rotate it so that we can always just assume any point x should be sit as a real line between 0 and 1, and let's strictly less than 1, and the other component should be 0. And one can also flip this like the order if one need, but it's not necessary. We just use this order. If there's no question. So then what we need to see is
Yeah,
because
here the atomeric group of bidisk is homogeneous. I mean, bidisk is a homogeneous domain, right?
bidisk itself is homogeneous for sure, but
Yeah.
symmetry bidisk is not homogeneous.
Okay.
So if this is a homogeneous like the space, then this calculation not interesting because this is already actually known for the Bergman metric. But the symmetry bidisk is not homogeneous, so that's why it's worthwhile to proceed exercise. So this map gives the non-trivial effect of the geometric structure. As you pointed out, this is homogeneous, but this is not. And also, it's worth to point it out that for the symmetry polydisc from the dimension greater or equal to 3, Carl Theodori and Kobayashi are never equal. Never equal. And I do not know, and also they are not symmetry, they are not C-linear convex domain from dimension greater or equal to 3. I do not know whether or not Carl Theodori and Kobayashi are equivalent. The known result only indicates that these two metrics are not equal as dimension 2. But other than that, no result seems known. So this is also interesting, like the direction of the investigation. But here, I just want to point it out that in order to proceed the curvature calculation with respect to the Bergman metric, I mean, one of the invariant metric, so one just need to look at this point because others could be recovered from the automorphism. And for the automorphism orbit, curvature value should be equal so that we do not need to care. So it suffices to check these points. So now this is a real one variable. So this is very doable in that sense. All right. So then what we know is the Bergman corner with respect to the coordinate of d cross d is also known. So that also is known for the Bergman corner expression with respect to G2, like the coordinate, but it should be handy that we can just write down everything in just a Z1 comma Z2 because they are completely like independent. So that this should be sort of the handy so that we start from the form of the Bergman corner with respect to this coordinate. So that you can just assume we just choose one just a handy coordinate to proceed the curvature calculation. So now we have this form. So others are just the calculation. So let's just see what we know. So what we know is the form of the Bergman metric. So what is the Bergman metric? So we know, so others are just nothing but the calculation. So we start from the log of the Bergman corner on the diagonal entry, and take the complex Hessian, and that gives the Bergman metric. And all we just need to do is to just proceed the calculation at x comma 0, where x is between 0 and 1. And by just doing the calculation, then this just follows. Either from the hands for sure, but also using the either Mathematica or whatsoever. So this is just coming from the calculation. So then now we know the Bergman metric form. Of course, it does not mean that we can simply just use this in a sense that our curvature calculation is a derivative calculation. So it should be taken with respect to Z1 and Z2 in general. And then we need to plug in because we cannot start from here because we are evaluating the derivatives, not just the function value. But anyhow, this is the form of the Bergman like a metric component. Let me now go further. Then also, as long as we have a metric components, then we also have the inverse component as well. It's just a AD minus BC of the inverse like the metric form. This is good. And now, in order to proceed the curvature calculation with the explicit coordinate, then one can just proceed the so-called Crispr symbol calculation. So if you already know the Riemannian geometry, then this convention is quite like the universal in a sense that, so for the left-hand side, we just fix each like the indices ijk. Ijk runs 1 and 2 because this is a complex dimension 2, so that there are now 8 choices basically for each ijk. So for fixed ijk, so ijk are fixed, and if the indices repeated twice, then this always means the summation. So that this is a summation with respect to L from 1 to 2. So it's just a summation of 2 terms in this case. Then we know what this is and also what this is. And we just need to proceed the calculation of the first derivative and just add them with respect to L. that is our Crispr symbol expressions, 8 components at this point by just using this form. And this form is also the case of the K. So if we have a Kähler metric, the curvature Crispr symbol has this form. This is the same form of the Crispr symbol with respect to the Levi-Civita connection. And now we are using the Chern connection, but it is the same as we are now working with the Kähler metric, because Borger metric is Kähler metric. So then now we get this. So it's also just coming from the explicit calculation. So as we know, just a metric form explicit. This is also okay. If you have any questions or comments, let me know. So next, so all now we need to do is the calculation of this guy. You can just think about the in this way. I might not proceed the form here. However, so one can either just using this expression of the curvature components or Riemann curvature tensor, just to show you the form so that you can convince yourself. All right. So if you like the search the known form of the Riemann curvature tensor, so that we are now evaluating these kind of things basically, and there's also a way to calculate this around in terms of the Crispr symbol. So the curvature components is known as a first order derivative of the Crispr symbol with some like a components of the Crispr symbol. So by using either this one or the expression I share, either one. So there's just a way to just calculate, just proceed by either using this one or in terms of the Crispr symbol. But I use the Crispr symbol in this calculation so that one also will get all curvature components. So just try to just match everything correctly. Just that's it. Then these are just some complicated expression of the rational function, and just that's it. And once one know the curvature components, then one is ready to calculate the range of the Holorn sectional curvature in the following sense. Now we have a global coordinate already, Then in order to know the curvature range, one can just proceed the Gram-Schmidt procedure to build the orthonormal basis, so that you can see this is just a Gram-Schmidt like a procedure that one take the first the unit vector field, and this is a natural just second vector field as we know each of the components explicit. Then, because we know all these expressions and also normalize, all those are just explicit, so that one can just proceed the calculation. Then this is just one of the specific choice of the pair of the orthonormal basis. So this calculation is not sufficient to conclude the range of the curvature, but still one should see this. So this H stands for the Holorn sectional curvature with respect to this specific orthonormal basis, then one will get this at this point. So that in this specific like the basis, one can just conclude from the calculation that so one can say that curvature sit inside of the negative range, and as x goes to infinity topological boundary, then the curvature tends to negative one. So it just comes from just a explicit calculation. Okay, so this is good. And now what one should do is, by the way, now we have an explicit form of the orthonormal basis, so that one can also calculate the bisectional curvature with respect to the Holorn plane generated from this x and y. So this is R of x bar and y bar. So this is also explicit for sure, because we already know all the curvature components. So it's just a linear combination of them. Then by using the explicit form, one can conclude that this bisectional curvature of the Holorn plane generated from x and y, this is even positive. So this is in this like the calculation first example that does not administer either the product structure or the homogeneous like the space structure, but the Holorn sectional curvature is negative range, but bisectional curvature does not admit the sign. This is the first example of the complete such like Kähler metric, and now there are also other like the possible like the components of the curvature with respect to x and y. So it's also coming from the explicit calculation that can be done. Now, this is a major part. So that now one need to generate the arbitrary unit vector field. So we have already orthonormal basis x and y. Then one should like to rotate to generate the arbitrary unit vector field. So this is corresponding direction. And in order to make it a unit vector field, because the x and y are also already orthonormal, so one just need to make this condition to happen. So a and b are complex numbers. So that this is the condition in S3. So with these arbitrary choices, then one need to proceed the expression of the Holorn section curvature. This is a Holorn section curvature. Then by using the linearity of this tensor, so that one will get this. And one should get 16 components of the curvature, like the components with respect to x and y, but they are already all known from the previous like the lemmas, so that one will get this. So that the arbitrariness sit just inside of this A and B. Then one should use so I uses the MATLAB before with the tracking this with the expert when I just post this on the archive. Then just we only need to check everything with the explicit components to really check the curvature like the range, and curvature range just satisfy the condition of the being negative. And that's what I did in this paper. This is just indeed just explicit calculation. And from Wu Yao's theorem, if the Holorn section curvature of the complete Burgon metric has a negative Lecter range, then it's known that it should be equivalent to the complete Kähler-Einstein metric and also the Kobayashi metric. This follows from the Wu Yao theorem directly. Then we already know that Kobayashi metric is same as the Cartesian metric. So four Immer metrics therefore equivalent. That's the way to conclude. And this theorem this paper from this calculation conclude that the Holorn section curvature has a negative pinch and Holorn bisectional curvature is positive. And one can also proceed a similar calculation for the other the types of the domain. So there are just two things I want to explain and share. So for the complex dimension 2, if the explicit Borg-1 corner is known, I think the similar calculation can be made very similarly, in my opinion. So even for the just a computer with not the supercomputer, one can proceed this calculation explicit from my own experience. From dimension greater or equal to 3, especially dimension 3, the calculation becomes a little bit monster. So that it's just very hard to just calculate the range of the Holorn section curvature in general. So in that sense, I'd like to share also one like the curvature calculation in my this publication. So also Alan knows this very, very well. So yeah, Alan, if you have any
Just to
comment.
add a point to it, the good point about this using the automorphism to reduce the number of variables on which the calculations are dependent is reduced by two. Basically, one coordinate is moved to zero, so the two variables are gone, two real variables are gone. In the other, by rotation, we can bring it to reduce it to the real level.
Yep,
So
exactly.
what happens is in the case of complex dimension 2, we have complex dimension 4, and it is reduced to 1. And as complex dimension keeps increasing, the number of real variable on which it should depend increases by 2 at least. So even for three-dimensional complex thing, the real dependency will be on three variables with constraints between them. So the calculations are really, as you mentioned, probably using some supercomputers and running the calculations. It should be doable for n equal to 3, but for higher, it might get more and more difficult. Even though if you supercomputer and get expression for 3 dimension, the expression that we get might be too big and too complicated to even put it on a single page sometimes.
Yep, exactly. So
Just
yes.
the point I just felt like adding.
Yeah, thanks for the comment. Yep. It's just the nature of so how the calculation should be more complicated. And in that sense, that's interesting. If you can capture some like the geometric structure to reduce the computation, that should be good. So one just need to find a way to do it. So Bharathi, if you have any comments or questions, let me know. Otherwise, I will share. So
Yeah, I have a question. Is it symmetric by disk is simply connected,
it is simply connected. So that can be
but not a C convex, right?
I think it's a C linear convex.
Oh,
It's also simply connected. So that can be checked from the description of the domain. So you can also find it from my paper. So for the conclusion of the equivalence is just different like the issue, but one can just use this like the specific type of the homotopy that just
okay.
just the t go to 0, so that this is contractible. So therefore this is
It's a contractible. Oh, nice.
Mhm.
Actually, I'm trying to give a counter example for some problem.
Sure.
Yeah, actually, what I'm working the zero. My second project is about describe the zero-dimensional fixed point set of a holomorphic function.
Is
Am
the
I audible
connectedness
properly?
matter for you?
Yeah. What about now? Am I audible now?
So is the simply connectedness has some
Yeah, actually, yeah. Mine is I want to work the zero dimension. I'm working in zero dimensional for bounded domains, and for convex domain fixed point sets are holomorphic retract, right?
Yep.
So then in that case, it's easy. So if you assume the fixed point set is zero dimensional, then it has only one point. So for the strongly pseudo-convex domain with the real analytic boundary, so there are only finitely many fixed points. So actually, what I'm trying to give, I want a non-convex domain, and I want to produce a uh, uh, I want to produce a biholomorphism, automorphism, which has two fixed points or three fixed points like that explicitly. I just That's why I asked whether it is
I see.
simply connected or not. So I
Yeah.
just want to give an example.
I see. Yeah, for like the set of the holomorphic function satisfying certain parameter, either the fixing some points or like the fixed points. So yeah, so those are highly non-trivial to really know the information.
Yeah,
So
actually, the reason why we are working in zero dimensional, one dimensional is we have only uncountable fixed points, right? So the next case is we have to work the structure of the fixed point sets. But if you assume the zero dimensional object, zero dimensional set, then we can explore whether it is finite or infinite. Kind of.
I see. I'm wondering about that, like the arguments or how it goes for the like a zero
Yeah,
dimension.
actually, we have started with first we are extending the automorphism, uniformly extending the automorphism group beyond the domain. And we used a Kobayashi distance. We want to show Kobayashi's locally unique geodesic space. Even we wanted to describe describe the domains, which is describe the Kobayashi hyperbolic domain, which has locally unique geodesics exist. Locally, I don't want globally actually.
Okay, I was just wondering to ask you, so what's the like the definition of the
Local geodesic, right?
Yeah.
Yeah, local geodesic. If you take any point, there exists a neighborhood, and take any 2 points in the neighborhood, there will be a geodesic. I'm not asking a complex geodesic. I want a real geodesic. Minimal path.
So geodesic with respect to what? With respect to Kobayashi?
With respect to Kobayashi, yeah.
Okay.
We wanted. So there we are in metric geometry. There is one concept called cat K spaces.
Okay.
Cat zero space like that, Alexander space, all this.
Yeah.
So there in some particular class of domains has such a property. So now we are going to explore what are the Kobayashi hyperbolic domains, which is a cat K spaces and all. So now I'm particularly working on that area.
So the idea is for the cat zero, like the space, there's a specific like a property of the locally like the geodesic like the space. So they wanted to just make some analog or some similar like a property for the Kobayashi like the hyperbolic like some of the classes of the Kobayashi hyperbolic domains.
Yeah, but the local existence is true for a Riemannian manifolds and because they have a exponential function is locally diffeomorphism, so we'll get a minimal geodesic path. So for that, for Riemannian manifold, it is true, but we are exploring for those domains, those hyperbolic domain which has such properties.
I see.
In my first project,
Riemannian one, the problem.
Yeah. In my first project, is it okay if I share this?
Absolutely, yes, please.
Yeah, in my first project, we have given a new and geometrical proof of if you have automorphism with three fixed points for a hyperbolic planar domain, then it has to be identity. So we have a simpler, we gave a simpler geometrical proof for the problems using Kobayashi. We have proved that our main result is Kobayashi balls with respect to Kobayashi metrics are finitely connected. The complement has finitely many balls.
So if you don't mind, can we just look at your like the paper with the
Yeah,
state?
it is there in archive. Maybe you can share.
Yeah, you
It is
can,
there in
you
archive.
can share
Yeah,
it.
maybe I
Well,
will. Oh, yeah, I will share.
mhm. I found your paper from archive that you posted on last like the February, right?
Yes, exactly. Is it visible?
Yep.
Yeah, this is the paper which we worked in the first project. So here we have proved that our main result is ball under invariant metric or invariant metrics on hyperbolic planar domains are finitely connected.
Mhm.
So here and using this result, we have proved some classical results on conformal mapping. The one is any conformal self map of a hyperbolic domain with three fixed points is the identity. And also we have proved the isotropic group of a hyperbolic domain is either finite or a domain to be simply connected. So we have used these applications. Our proof was simple. Simple in the sense that we know the automorphism group of the finitely connected domain. It's just automorphism, right?
Yep. Mhm.
For automorphism group of finitely connected domains is just Mobius transformations. So if it is a three fixed point, then identity. So what we have done, we have started with a hyperbolic planar domain, and let's say if be a conformal mapping which fixes 3 point, we find we choose the one fixed point, and we consider the Kobayashi ball containing all these three fixed points. So this is we can construct such a ball. I mean, obviously we can choose such a Kobayashi ball with respect to Kobayashi metric. Then this is a finitely connected. We can restrict the automorphism to the ball, and we know that Kobayashi is invariant under the automorphism. So finally, the automorphism which takes this Kobayashi ball to that Kobayashi ball, because we have a one fixed point, right? You say here we have a fixed point, so it does not. It takes Kobayashi ball with respect Kobayashi ball around point A, and the radius is R. That conformal map takes that domain to itself. So now we know that such a automorphism has to be Mobius transformation, and we have three fixed point. It has to be identity. But then identity theorem it takes identity.
Oh, that idea is clever.
And we have shown this why all Kobayashi balls is finitely connected. We used Van Kempen, the argument which we used in Van Kempen, right?
Idea is
So
quite clever. Mm. So you uses the so basically two different structure with the overlap. We have a automorphism group entirely and also the automorphism group of the unit, just the ball, and then you
yes,
play with it by using the fixed point nicely.
yes. If main point is we have fixed points, then only because of that we can map the ball with ball
Right.
maps itself.
Oh, that's something. That could be quite useful, not just the planar domain case, but you use the property of the planar domain. Essentially,
Yeah, exactly, because I used a covering map argument to prove that Kobayashi balls are finitely connected. Actually, we covered. Maybe I can show the sketch of the proof here. Yeah, here is the proof in theorem. So we started with the Kobayashi resistance on R. D is a Kobayashi resistance, and we have started with a B, B a open ball and the B. And we know that B closure is complex subset of R. Then we know that R is a hyperbolic domain, right? So we have a covering map. We have a covering whose universal cover space is unit disk. So we have a covering map. So our aim was to construct our aim was to construct just a minute where we construct a finitely many disk around we take a full back of the ball. We started with a ball, right? Open ball of radius r. Then we take a full back, we'll get a disk in the unit disk, right? So look at here. Is it visible?
Yeah. I will look at your
So
code.
yeah. So P of D closure is B closure, right? So it is true. One can be prove easily this covering map always takes a ball with respect to the point array is same as the ball with respect to the Kobayashi. I mean, is equal to the. It takes ball to ball. It takes to ball to ball. In domain we have a point array. Here is a Kobayashi. So here in Poincare geometry, that here the ball is just a disk. We can realize as a disk. Okay, so what we are trying to for each x in the disk, we can find a dx such that P is an isometry on the dx because covering map is by locally by holomorphism, right? So we are trying to cover D closure by such disks first, and here the radius can be different. The radius can be different. The radius of dx can be different, right? But what we want a unique radius. So we used a Lebesgue covering lemma to get a fixed radius. To cover fixed radius such that P is an isometry on the every open disk of disk radius are under the Poincare distance center at some point of D closure. So we have covered D closure by finitely many disks of radius, fixed radius. Now we use the compactness, and we reduce the radius. To cover the D closure. And what we have done, we enumerate such a disk. And we taken a D to be, we will get a D using the union of DI intersect D. See, actually, we cover the D closure, right? We cover D closure by a finitely very part. But we can cover D union of that ball intersect with the D, right? So this one. Second one is if you consider this ball, if you take two such balls intersect with the D, always path connected. In fact, intersection to be convex here. We can do such a manipulation.
Okay.
And each ball, if you restrict, now we have a finitely many disks Di. If you consider Di intersect D, if you consider the image of the Di intersect D, we'll get a open by definition of the covering map under the Kobayashi distance and the Poincare distance. So this is a simply connected because we have choose the covering. We have choose the cover in such a way that the covering map is isometry, right? So isometry in the sense that simply connected is invariant under the biholomorphism. So the each B is simply connected and the intersection is at least simply connected. But we don't know whether it is convex or not, but we'll get a simply connectedness wherever the intersection to be non-empty. So this is our required cover. So then rest of the proof follows from the idea follows from the Van Kempen theorem.
Yep.
Start with a.
For me, it's been a while to look at this argument. Yeah, but I know what you mean. Yep.
Yeah.
Yeah, this is very nice. Yeah, as you already pointed out in your remark, yeah, this looks quite general. Mm, I should look at this for a couple like the days to think. So yeah, so this is something. Mm. Yeah, thanks for sharing the argument in detail.
Yeah, thank you. Actually, we have submitted in last year. So after 9 months, it got rejected by in the Journal of Analytic Sciences, Suplo Normalized PISA,
It's just a
some
bad luck.
Italian
Yeah,
journal.
let's move on. It's fine. Yeah.
So then we have submitted the Journal of Geometrical Analysis in the month of January 2025.
Yeah, we should best of luck. So, yeah, should be very worthwhile to get published. But yeah, I wanna think about this for a moment. So
And we have proved analog results for cathode also. In general, cathode also need not be connected.
mhm.
It's not behaving like as Kobayashi balls. So we have started the component. We have discussed about components of the Kobayashi balls. And we have the applications, list of applications.
So I
Some
will
few
get
applications.
this paper for incoming week, and next week I will just share my my feedback on the
Okay.
detail. So yeah, I think this is very worthwhile for me to look at the detail and try to imagine so how can actually one can go further.
Yeah, based on this paper, we have extended the fixed points argument to the higher dimension. So we are interested to discuss zero
I see,
dimensional
I
objects.
see. Yeah, that's natural like a direction to proceed. But yeah, I wanna like
And we are trying to use this finitely connected argument for the Riemann surfaces. Actually, here we have shown something different. Kobayashi ball of a hyperbolic domain, hyperbolic Riemann surface is just the fundamental group of the Kobayashi balls of the hyperbolic domain, hyperbolic Riemann surface is finitely generated. Actually, our group is using the Van Kampen theorem. We have shown that the fundamental group of Kobayashi balls is finitely generated. Since we are in the planar domain, then it has to be finitely many volts because the fundamental group is finitely generated, right? So that is our idea. So here we have actually our main proof is the main theorem is I will show the statement first. Maybe that will be better. This is the statement, the theorem 4. So R be a Kobayashi hyperbolic Riemann surface, then the fundamental group of each ball under the Kobayashi distance is finitely generated. In particular, the balls under Kobayashi distance of hyperbolic planar domains are finitely connected. So using this technique, we are trying to prove that the fixed point sets of a compact hyperbolic Riemann surface is 2G plus 2 bit at most. So we have tried, but we have there are many things is unknown. So here we used behavior of the automorphism group of the finitely connected domain, and but there is everything unknown. So we kept it as a as of now.
yeah, thank you very much for sharing this your result. I feel it's very interesting. So for today we can maybe finish the converse discussion here, and I will look at your paper for a couple like the days, and you guys
Yeah,
can
sure.
look at the either the Lampert theorem or some like the Bergman corner relevant like the pieces, and we can discuss next like the Saturday, Sunday.
Yeah.
Okay, yeah. Let me stop the record.